Okay, so in the previous class, what we did was we were talking about projective resolutions and how when you have a projective resolution of a module M and you have another resolution, not necessarily projective of a module N, and you have a map between M and N, then this map can be extended to the resolution. Okay, this is what we were trying to prove. Here was a formal statement of it. And then we started talking about it, and we were showing the existence part, and it was an inductive proof. And the strategy was to, well, again, use the property that if you have a surjective map of modules, then it lifts to a map from the projective module. So we had a diagram like this, and then went down here. And so also last time I was talking about BNs versus ZNs. In this particular application, I realized it doesn't matter because the resolution was assumed to be exact, right? So that, I mean, by definition, resolutions are exact. So the kernel is equal to the image. So it doesn't matter if we used BNs or CNs. And so this sequence would be exact with BN or with CN. All right. So what it remains to show is the uniqueness up to chain homotopy. So that's what I'm going to prove now. So uniqueness. Okay, so again, we're going to suppose that there exist two maps, right? So let me start here. All right. So suppose we have two maps. All right, F bullet and G bullet from P bullet to Q bullet are two chain maps lifting this map F from M to N. And we called this map F minus 1 last time. Okay, so what we'll do is we're going to construct a chain homotopy between them. So we will construct some H bullet. Okay, so from Pn, okay, we'll do this for each n. Pn to Qn plus 1 for each n, such that, all right, F minus G at each n looks like DH plus HD. Okay, so I think we wrote down what this looks like somewhere. Yeah, it's one of these things, right? So we're going to have a map going back, right? And in this, you know, F minus G is going to be D then H, or H then D. Okay, so there's one going to the left, which you do H first, and then there's one going to the right, which you do D first. But you add those two together, and then you'll get F minus G. Okay, so that's what we're trying to show. Okay. All right. So we're constructing a bunch of maps that go backwards. All right. Okay. So all right. So for n less than or equal to 0, so we'll do this by induction. Okay. So for n less than or equal to 0, or less than 0. Okay. So for this, in this case, we're just going to use, so we have the 0 map. So we have, so since Pn is equal to 0, for n less than 0, the map Hn from Pn to Qn plus 1 must be 0. All right. So in particular, this means that H of minus 1 is 0. Okay, the only thing from a zero module is the zero map. Okay, so now let's do the base kind of the base case here for n is equal to 0. Okay, so what we will need to construct a map so we need to construct H0 H0 goes from P0 to Q1. Okay, and it fits into the diagram like so. So here's what we have. So we have P0, we have Q0. Okay, so then we have F and G, F0, G0. So we have the D map. Here's P1. Here's Q1. It also has a D map, just different map, same name. There's two maps here, F1 and G1. And so what we want to do is we want to get this map here, H, the one that I just labeled with a question mark. Okay, and of course these fit into their resolutions, M, eta, N, and this is the map F minus 1. It's also the same thing as G minus 1, and this is what we just called the map F. Okay, so all right, and so let's look at what happens here. So so eta. So again, okay, so let's look at what happens. So eta of F0 minus G0. Okay, so that's this map down here. So we apply F0 minus G0. So that's a map from P0 to Q0. Okay, and then we apply eta. Okay, and this diagram commutes. So this is the same thing as F minus 1, G minus 1, epsilon, but F minus 1 and G minus 1 are the same thing. They're F minus F epsilon, and this is 0. Okay, so what does that tell us? So that tells us that the image of F0 minus G0 is contained in the kernel of eta. Okay, but because this is a resolution, this map eta here, that's the kernel of eta is actually equal to the image of the map Q1 to Q0 above. All right, so that's equal, and let me just say they're equal by exactness. All right, so this thing here is what we call the cycles of Q. All right, I'm omitting the bullet. I'm going to start to omit the bullet more often. And then these are the boundaries of Q, B0. Okay, so they're the same thing because it's exact. Okay, so all right, and so what does that tell us? So now we want to be in a situation where we can apply the lifting property. Okay, so let's kind of figure out what diagram we can write down. So the diagram we can write down here is with the cycles. So here we have P0. This goes to Q0. Okay, so this is F0 minus G0. And then let's see. So let's actually get rid of this. Let's do the cycles here. We'll do Z0 of Q. Okay, and this goes from Q1 here, and okay, and we want a map like this. Okay, and notice that this map is surjective. Okay, so this map's surjective. By definition, right, this is B0 of Q, and this is by definition the image, so it has to be surjective. Okay, and so this is a surjective map, so this thing here exists in H0, so this is by the universal property of projective modules. I don't know if it's the universal property, let's just call it the property of projective modules. Okay, so P is projective, so this thing exists. Okay, and so let's read off what the diagram says. so the diagram here says that, well, D, so this is the map, this map here is D, right? So it says D of H0 is equal to F0 minus G0, okay? But we can also write this out, right? So this is not isomorphic, this is equal to, okay, so DH0 plus H minus 1 D, right, by definition. So that shows that this proves the homotopy, this kind of base case step. This map here again was the zero map. Okay, so this holds. Okay, so that proves this proves the base case. All right, so now let's do the inductive part of this proof. Okay, so let's do the inductive step. So let's go down here. So the inductive step. Okay, so suppose we have a bunch of homotopies and we need to chain homotopies and we need to construct the next one. So suppose we have HI from PI to QI plus 1 for I less than N. So what we'll do is we will construct HI from PN to Q N plus 1. All right, so we have a bunch of them, and then we're going to construct the next one. So let's kind of let's introduce some notation to make things easier. So let's just make some notation here. F n tilde. So this is just going to be Fn minus Gn. Okay, and we're essentially trying to show that this thing is null homotopic. Okay. Okay, so let's draw everything out. So we have Pn plus 1 here. We have Qn plus 1. And we have this map F tilde of n plus 1. Okay. We have Pn here. We have Qn here. We have Pn minus 1 here. We have Qn minus 1 here. We have Pn minus 2 here. We have Qn minus 2 here. Okay, and then we have all the maps here, the tilde maps. These are the differences between F and G. And then we have the D maps going this way. Okay, so those are all the D maps. And then we have homotopies here. So we have Hn minus 1, Hn minus 2. And what we're looking to construct is we're looking to construct this one, right? The Hn plus 1. Okay, and so what are we going to do? Okay, so let's look at what the chain homotopy property says. Okay, so the chain homotopy property, it says that, well, at least in the n minus 1 case, right? It says that this thing here, so this is this map being null homotopic, right? Plus Hn minus 2D. Okay, so it says that this Fn minus 1 tilde is D of Hn minus, so it is D, let's see, Fn, okay, so it's D, oh, sorry, Hn minus 1 here, then D, and then it goes D, then Hn minus 2. Okay, and you add those together and you get Fn minus 1. All right, so that's an equation that we have. And so we can look at what DHN plus 1 looks like to kind of guess what DHN is going to look like. So DHN plus 1, or DHN minus 1. Okay, so that is Fn minus 1 tilde plus Hn minus 2D. Okay, and so like so what we're going to guess is, right, so if we want this to work, right, so we're going to need DHN to be Fn tilde plus Hn minus 1D. Okay, so this is kind of like what we want to happen for this Hn that we don't know exists yet. Okay, and so let's just look at this piece. So let's study Fn tilde plus Hn minus 1D. Okay, and let's see if we can construct the map Hn from just looking at this piece. Okay, so so first let's take D of it. D of Fn tilde plus Hn minus 1D. Okay, so what is this? This is D of Fn tilde plus D of Hn minus 1D. Okay, and now we can use our previous expression here. So this is D, or let's go like this. Let's do this one here. All right, so this is D of Fn tilde plus, okay, and now let's replace what we had before. So this is Fn minus 1 tilde plus Hn minus 2D, and then we compose that with D. So this one's going to give a D squared, and so this is D of Fn tilde plus Fn minus 1 so let's see. I think I'm missing a minus somewhere. This is a minus here. Minus here. And this is a minus. Okay, so then this should be a minus. 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 Okay, that's tilde. And D here. So I think that's all we have here. So, okay. And so, okay, so this thing ends up being 0. Okay, why is this? So this one is from our previous equation, right? Okay, and then this is because Fn tilde is a chain map. That the diagram commutes with the Fn tildes. So this thing is 0. Okay? So, okay, so what does this give us? So now we have kind of like a situation similar to the base case, right? It says that for all x in P of n, right, Fn tilde of x minus Hn minus 1D of x, right? So this is an element of Z and Q. So D of it is going to be 0. Okay, and so let's write out what the situation looks like. The current situation. And let's see if we can apply the property that projective maps have. Okay, so we have a map here. So we have a map from Pn. Okay, this goes into Z and Q, like so. And this is Fn tilde minus Hn minus 1D. Okay? Okay, so now we're going to use the property that the sequence was exact. This is the same thing as B and Q. And this is a surjective map. Okay, so we have a projective module here and the surjective map. So what do we get to do? So we're going to define the map that lifts the map that lifts this thing. Okay, so here, this is the definition of this thing. This is by definition. It exists. Definition. Okay. It's going to be that there exists some map like this making the diagram commute. Okay, and let's check that this thing, D like so. Okay, so let's see what this diagram says. So this diagram, so this is my projectivity. Pn is a projective R module, so this thing exists. Okay, and so now let's write out what this diagram says. This diagram says that D of Hn is equal to Fn tilde minus Hn plus 1D. Or it says that Fn tilde is equal to, well, D of Hn plus Hn plus 1D, right? And so this is what we wanted to prove. Okay. All right. So, all right. That's the end. We showed that we showed that the two maps. So this proved that F and G were homotopic. They're chain homotopic. Because we showed that F tilde, which was defined to be the difference for those things, was null homotopic, and that's the definition of being null homotopic. Okay. So yeah, and so that completes the proof that. So what's the proposition that we proved again? Let's go back up, way back up here. So again, it says that if you have a projective resolution and you have another resolution and a map between these, then this map lifts to a map between the resolutions. Okay. All right. So I want to cover some. Okay. So what are the things that we're trying to do? So we're trying to prove functorality of X and Tor. Okay. And so we need properties of projective resolutions like that. But I also kind of want to give an idea of what's going on in some of these proofs. So I am going to stop and say a little bit about that. So I guess I'm going to stop the video and then make another video where I do that. So let me stop the recording.